Welcome, everybody. Good afternoon. I just wanted to do a little introduction of myself. For those of you who don't know me, I'm Sonia Hammer. I moved here from the San Juan Islands, where I was working in community solar, worked closely with the local utility there and with the Conservation District, developing a countywide energy plan, which we're trying to do here in Jefferson County. And I started volunteering with the Local 2020 when I moved here, and presently I'm working for the Energy LLC, developing a plan for a countywide electric vehicle program. I'd like to thank the sponsors, Steve Tucker, the port, particularly for the space that we're using today, Bob Grimm with Alaska Power and Telephone, Robert Urish, Sunshine Propane, Letitia Huber from Huber's Inn, and finally Andy Cochran from Power Trip Energy. And today we have Brittany, who would like to give a little plug for their solar tour.
Hi guys, I'm Brittany. I'm with Power Trip Energy, and I just want to let you guys know that we are doing our Jefferson Solar Tour and EV Roundup on June 9th. The kickoff location is Power Trip Energy, and we're hoping to coordinate all the solar, and we've got solar all the way around Port Townsend, so we've got homes lined up for people to come out and take a look at, and we have a presentation, and we're hoping to get a bunch of electric vehicles to chaperone our guests around to make it a clean energy event. So spread the word, and thanks for having us. Thank you.
Okay, and next month, third Thursday, as usual, June 16th, we have George Mobus, brought to us from Eric Tays with the port. George Mobus is a professor at UW, and he's talking to us on the application of system science principles to Jefferson County energy, environment, and economic planning. And that's all I have. If anybody else has any other announcements today. And I just wanted to give you a little reminder that if you have questions, hold them till the end and come up and use the mic so they get recorded. Today, we have Jeffrey Budd. He is going to talk to us about electrolysis and the pathway to carbon-free fuels. Jeffrey worked for Degussa AG for a total of 19 years in various positions. He was Degussa South Africa's GM of sales before emigrating to Germany as the export marketing and business development manager in the emission control catalyst division. He worked in North America and Asian markets for the company. He then moved to Canada as VP of Degussa's Canada's Catalyst Division, and then he emigrated to the United States in 1995 as the Global Key Account Manager for a number of the automotive OEMs. Jeffrey relocated to Vancouver in 1999 to join Ballard Power Systems. He held the positions of Key Account Manager for the company's automotive OEM customers. He was the chairman of the board of Ballard Power Systems in Germany before its sale to Daimler and Ford. And he was the managing director of Ballard GmbH in Stuttgart. He moved back to Vancouver in 2008 as the European Director of Business Development and Sales. He then joined ITM Power Team in the middle of 2012 as the company's business development representative for North America and the market segments of clean fuel and energy storage. He's going to talk a little bit today about his presentation at the NH3 Fuel Conference in 2014. Jeffrey has an honors bachelor's degree in science from the University of Natal in South Africa and an MBA from the University of Witwatersrand, Johannesburg, South Africa. He attended numerous executive business courses in Germany, Switzerland, US, and Canada, and he is fluent in German. Please welcome Jeffrey Budd.
The organization that I represent and do business development for in North America is called ITM Power. It's a small company. That's great because we're flexible. It's a very flexible entity in terms of getting new things, new stuff done. The company is based in the UK in Sheffield, the old steel centre of the UK. The organization, in fact, is public. It went public in 2004. And we set up companies in Germany for obvious reasons, in California for obvious reasons, because of renewable energy policies and mandates and regulations. As I mentioned, very small, 75 odd people. We also have folks in Germany at the company. We have a guy who runs and does our work in France, of all places. Even though they have 49, 50 nuclear plants, they're also thinking about renewable energy for the future. Our largest, we have two very large shareholders in the company, and I don't know whether JCB means anything to you folk, but it's the UK equivalent of Caterpillar, who produce heavy-duty equipment. And the other big investor in our company is the Allianz German Insurance Group. So those are the two big heavy hitters we have supporting our activities. Okay, without further ado, I told you I'd tell you some stories. I picked this up, in fact, on Monday. And without reading through it for you, it's really interesting in that Germany's energy policies and the enactment of what their policies, in fact, were set out many years ago, are starting to show some really interesting signs of achievements. Sunday, this last weekend, the Germans actually produced from renewable energy roughly 46 megawatts of power. Gigawatt. Did I say mega? Giga, beg your pardon. 45, 46, and their demand was just slightly higher. So in essence, what they had achieved on Sunday this last weekend was providing all of their demand requirements with renewable energy, which is a huge milestone, right? So Angela Merkel is obviously on the pathway of making it happen. She was the chancellor that really put into place the photovoltaic and also the wind and stopping the actual nuclear power plant production of energy in the future. So that's the story. In the presentation, there's a link to the Bloomberg article, which is quite interesting to have a look at in terms of this particular milestone. So I thought I'd throw that in just to show you a bit about what's going on in other parts. So what does our company do? We make hydrogen. And the key is to make hydrogen out of excess energy. And excess energy, I'll show you some graphs a bit later on. When you have an abundance or a predominance of renewable sources, you end up by having a very variable supply and also, in many cases, large excesses which are currently being curtailed. And the idea is, what can we use those assets for in terms of not being curtailed and storing the energy? So we'll talk a bit about that. And the businesses we're involved in are fundamentally generating hydrogen from excess electrons and then using that hydrogen for a value chain that makes sense. You can actually use the hydrogen to generate electrons if you wish. It's not a very efficient system, but it's an opportunity. You can also, we'll talk a bit about that later on, is use that hydrogen for the production of ammonia, for a fuel or for fertilizers. The other part of our business, and we were talking at lunch about electric vehicles, I'm a fuel cell electric vehicle guy because I don't want to sit around for 3 hours and charge my car. I'd rather fill it up in 3 minutes and drive it away and have a range that will happen when it doesn't get cold. Nevertheless, I think battery electric vehicles are going to find a place. We, however, support the provision of hydrogen for the operation of fuel cell electric vehicles. We'll show you a few pictures of what's happening in other parts of the world. So that's what the company does. What we make and what we deliver as the fundamental products into the marketplace are PEM electrolyzers. Now you might ask, well, electrolyzers have been around for decades. What's new? So the electrolyzers of the past used a specific type of membrane that, when the product was used, operated the product at a stable, constant level and provided hydrogen from electrolysis primarily as a feedstock for the chemical industry. And what has basically happened is now electrolyzers are being pulled more into the energy industry, which means they have to be capable of accepting variable quantities of energy supply to produce the hydrogen. So they become demand response type products. And the technology that we and others, including companies like Siemens, are now producing are PEM electrolyzers, solid membrane products. So for those electrochemists in the audience, ITM is an acronym for ion transfer membrane. And that's where the company had its foundation. is in fact in polymer chemistry, producing a membrane that is now used in the electrolyzers that they sell. A bit more about the pallets, just to give you an idea. We have a standard set of products that we deliver into the marketplace. Basically a 1/4 megawatt up to a 3.5 megawatt product, using state-of-the-art electrolyzer stacks to convert water using electricity into hydrogen and oxygen. We also have the ability to customize products in terms of size. And I've been in discussions with Bob in the last year plus, and things have changed since then in terms of our cost reduction. So things are happening pretty quickly in terms of us providing competitive products into the marketplace, serving the energy industry. So this is all sort of background information. Let's talk a bit about the rationale behind what we do and what we supply to the market in terms of being able to use that energy. Why hydrogen as a fuel? When you think of renewable energy and you think of a renewable energy chemical, what comes to mind? Hydrogen is probably the most abundant chemical fuel on the planet. The only challenge we have is that it's bound up in water. And that's what the electrolyzer does, is separates the hydrogen from the water. Separates the hydrogen, produces together with that oxygen. And that is basically how an electrolyzer works. It's simply a membrane in the middle, surrounded by catalysts, with electricity applied to specific electrodes on either side of the membrane. And on the one side, hydrogen is generated, and the other side, oxygen. So if you go back to for those non-chemists have I lost sound? Non-chemists in the in the room today, the school electrolyzers that we used to play with by putting 2 terminals into a beaker of water. Okay. Energy storage. A term called power to gas was, I guess, invented or founded by a German engineer approximately 15 odd years ago, when Germany started deploying a lot of wind energy, which generates electrons mainly at night as opposed to during the day, when they needed the energy. And as time progressed, they thought about ways and means of storing. How do we store energy that comes from turbines, or in the south from photovoltaic sources? And basically the guy said, well, we've got this, in their case and in many parts of the world, including North America, huge storage infrastructures. In fact, the largest energy storage infrastructure that we as humans on the planet, in fact, have installed on natural gas grid networks. So, for example, in North America, our gas grid networks store roughly 60 days of energy. I'm not too sure whether you realize that, as opposed to only delivering it to us, to the homes and industry, they store. The Germans store roughly about 3 months, and so did the folk in the UK. So it fundamentally provides an asset where you can store energy. And what has basically happened as part of the story across in Europe is that they store the hydrogen, not only as hydrogen, but into the natural gas grid network up to a specific percentage, and that's called power to gas, one of the pathways to power to gas. So when you look at the picture, on the left-hand side, generation, the actual electrolysis producing hydrogen. Of course, the oxygen has a value, but we don't capture it now. It's vented to the atmosphere. It can be captured and used. And then that hydrogen is either directly injected into the natural gas grid network as a storage medium to be used. Use your imagination, whatever natural gas is used for downstream. Or it is reacted with CO2, can be carbon neutral, preferably carbon neutral, from sources like anaerobic digesters, wastewater treatment plants, or farms, dairy farms. Any source that has anaerobic digestion of organic material is a candidate. and producing synthetic methane that then goes into the grid. And that's, in fact, there's a lot of work happening in Europe to help the grid owners also become green. In other words, to be able to provide renewable heat, which is the fundamental and primary purpose of gas grid networks throughout the world, is heat as opposed to electricity. So that's a bit of the actual background in terms of power to gas and one of the pathways, or two. Energy storage. Maybe some of you have seen something similar to this, but this is quite an interesting graph in that it talks about energy storage in a number of continuums from a technology perspective. So if you look at your far left, you see flywheels, and as you move up the order, you see batteries of different shapes and sizes, flow field batteries, compressed air, and in that large storage sector at the top right, pumped hydro, which is probably today one of the largest seasonal energy storage technologies, followed by, on the top right-hand corner, power to gas, either using hydrogen and methane, or synthetic methane. Now you might ask, why and how do we put hydrogen into a natural gas grid network? Because hydrogen has a totally different burning oxidation characteristic to what natural gas, primarily methane, in fact has. And there have been a number of studies on that, and there are limitations in terms of how much hydrogen you can put into the gas grid network before the flame burn characteristics, in fact, change. Now, in Europe, the country that has the highest limit is Holland, and for historical reasons, the lowest is in fact the UK, although 20, 30 years ago, the UK had town gas in their systems, which is roughly 60 to 70% hydrogen. So they are in, and the reason why those levels are existent today has to do with rules and regulations associated to the purchase and supply of natural gas from primarily Russia. The change in Europe is taking place where the natural gas grid networks will probably, throughout the European Union, be accepting up to 5% hydrogen in their gas mix, which will not change the calorific value of the gas and not change the burn or the flame speed characteristics of the natural gas either, but will provide terawatt hours of energy storage for example, from wind turbines that are operating and currently being curtailed. Okay? So I'm sure you'll have questions about that at the end. Here are some examples of the plants we have in place. This is the first one we in fact put in place. It's just outside of Frankfurt, east of Frankfurt, on the Main River. And we did this particular project with one of the largest utility companies in Germany, the Tuger Group, who basically operate as a consortium, a collaboration of various utility entities around Germany. And this particular plant takes excess energy and at a transmission distribution gas node, puts it into the gas stream up to approximately 3%. Why 3%? Because just down the road from this plant is a CNG compression facility that produces CNG for vehicles. And they asked to keep the level down because they have metal tanks in the cars. That's the gas mixing plant there for you. Our second project was with RWE, a very large German utility entity that is currently having major financial problems. They have got red figures on the bottom because they haven't really joined and are slowly coming on board with these new types of technologies that are being deployed throughout Germany. Just a really interesting one. We talked about district heating. This particular unit is quite interesting because it's at a transmission distribution node link up between transmission lines and distribution. They reduce the pressure, which means it cools the gas, and they have freezing and condensation. They use the heat out of the electrolyzer as well to heat up the gas so that that doesn't happen. So the efficiency goes up to about 90%. Two other projects that we have in terms of energy storage, completely different use of the hydrogen. This is quite an interesting one. Hydrogen is being generated from excess electricity. It's going to be stored and then used by the DLR, which is the German aerospace entity in Germany that looks at all of the future development of aerospace applications, including the use of fuel cells in planes as APUs. So we've delivered, we will deliver, I beg your pardon, a 1 megawatt unit to them, and they will be using excess electrons from the wind that's generated through the grid into this particular system to generate hydrogen for a number of sources, including fuel cells. This is a project that I think, Bob, you responded to it when you saw some announcements go out. We have a 0.5 megawatt, I've got a really nice map here, a 0.5 megawatt system that's actually installed at the European Marine Research Center in the Orkney Islands. And this is the first unit that got delivered. And the second one we will deliver during the course of next year. It'll be a 1.5 megawatt unit. And these particular applications are again a mixture of wind and tidal. The tidal plant on Edney will be feeding that unit. It supplies hydrogen, which will then go to actually fuel cell vehicles. They will also use the hydrogen with a fuel cell to back up their data center. So that is a critical resilience, a critical energy supply. They'll store the hydrogen in tanks and have that available to keep their data backup center going if they have some incumbent weather that shuts things down. The other plant here, in fact, on Shipsony over here, which will have, in fact, not a 1 megawatt but a 1.5 megawatt, will also produce hydrogen again for mobility. So again, this is all energy excess renewable that is being used for a number of purposes, and primarily in this case electric vehicles. The partners in this particular project, I took that one out. That in fact includes a number of companies, a number of pretty large organizations, including companies that make fuel cell vehicles. Power to gas. This is probably the largest consortium of energy storage power to gas organizations in the world. It's operated and managed by the German Energy Agency based in Germany. And what is really quite interesting is that they have a really comprehensive and well summarized description of power to gas and how excess energy from photovoltaic and wind is being developed and evaluated in Germany. And what's really cool about this, and we've talked about ammonia, and in this particular case up here, you will see that there is an industrial application for the hydrogen. We're not involved, but that is in fact the use of that value that is being generated for the production of ammonia, and not in the case of using it as a fuel, but as a fertilizer. When you have a look at this map here, the two plants that we have are in fact the Tuga, and the other one is RWE up here. And I talked about synthetic methane. This organization here, Fissmann, the Fissmann Microbe Energy, they also have another one, where is it? Allendorf, where their headquarters are. And you can see what is really very interesting about this technology is all of the pathways that you can in fact create a value chain with that excess energy that you're getting from renewables. So it doesn't have to be the injection of hydrogen to the gas grid network. It can be a combination of a number of things. And I'll talk a bit more about that as well as we move along. One of the ways, let's just talk a bit about generating synthetic methane. The production of methane is actually quite an old technology from a chemistry perspective. It's called the Sabatier reaction, and it's been around for a long time. What a number of companies are doing now, because, for example, in California, they have a mandate to decarbonize their gas grids. And the only way they can do that is to think about using that infrastructure with a green gas. So biogas or synthetic methane is the pathway that's being pursued. And this just provides you with, again, another opportunity using CO2 from wastewater treatment plants or breweries or distillers or folk that produce alcohol for fuels. CO2 is a byproduct, and it is relatively carbon neutral. Using that CO2 and reacting it with, again, generating renewable hydrogen from wind or photovoltaic or marine, whatever the source is, hydro, to produce methane that is then distributed back into the grid as an energy storage mechanism, and in the grid that has the huge storage capabilities. There is a biopath that's being developed as well by that company I showed you, Fisman Microbe Energy. There are a few companies, in fact, doing it that way. Let's move into the world of ammonia. I don't know whether I have that chart up here, but the production of ammonia as a fertilizer is the second largest consumer of, as a separate industry, of natural gas for hydrogen that is reacted with nitrogen in the atmosphere to produce ammonia as a fertilizer. And the European Union has recently challenged industry to begin working on moving that hydrogen from natural gas through steam, methane reformation into the world of taking the hydrogen out of water or from hydrogen, renewable hydrogen sources like biogas. And what we've done as an organization is that we've begun a project, which I'll show you in the next slide, that takes the hydrogen through a small reactor to generate methane, ammonia, which then gets reacted with CO2 to produce urea, which is another form of nitrogen as a fertilizer that's used primarily in Europe as a solid material. But this particular pathway here is really a very simple exchange of hydrogen from water, and then using that hydrogen to basically generate ammonia for whatever purposes are required, right? As a fertilizer or as an energy vector. The project that we have, in fact, underway at the moment incorporates two partners. The Waitrose Grocery Group that owns a number of farms in the UK, the University of Sheffield, who's in fact designing and developing the micro-reactor to produce the actual ammonia, and the other partner, of course, is us in terms of generating the hydrogen from an electrolysis unit. And looking at the actual pathways, what we in fact are doing is reacting the CO2. The concept is to take the CO2 from the dairy farms anaerobic digesters and use that CO2 to, in fact, so it becomes more of a sustainable cycle in terms of using what's available and using the excess energy from, primarily in the UK's context, wind, excess wind energy. This is just a further chain in terms of how the ammonia-based products, from ammonia to ammonium nitrate, that's a combination of urea, ammonium nitrate solutions, urea, and then ammoniated phosphates. Phosphorus is the other major fertilizer, phosphorus, potassium, and nitrogen. And those pathways are being evaluated by this particular group that we're working with. So we are involved. We've also got another project that we've applied funds for on this continent that I cannot say too much about at the present moment, but it's going to pursue pretty much the same pathway as we have here. But the chemistry is the same, making ammonia using the Haber-Bosch process and developing a reactor that's cost effective from a small scale perspective. Here's another interesting pathway. We talked a bit about it at lunchtime today in terms of what electrical grids require. So if you look at the left-hand side of the table, the diagrams, we move from base load or base producers of energy, electrical energy, from left to right, going through a number of variables that show you very clearly how responsive they are. So if you've got a nuclear plant or a coal plant and you have excess energy being produced versus demand, how do you turn it down? So what you do is you then have demand response customers who buy that energy from the source under specific contracts. And that's one of the other focuses that our organization is now looking into and in fact is adopting. And that's the use of electrolyzers, water electrolysis units that generate hydrogen as a renewable energy vector, and also act as a load on the grid to either absorb demand response or to operate and provide frequency regulation. So once again, in the world of ancillary services, to look at how we can generate revenue streams from that energy storage concept, right? From excess renewables that are coming onto the grid in greater quantities as we put more and more in place. And in this particular case, we use an electrolyzer. The first picture I showed you of the Tuga unit is actually registered in the German balancing market and is operated somewhere between 100 and 0%. That's always kept operative. So is the gas. And Minova, the utility company, who then is able to quote the system onto the market, it's an auction market, in terms of when frequency either drops or decreases, they can actually ramp up the load of the electrolysis unit or ramp it down. So they form a generation and a demand, a quasi-generation and a demand response product to serve balancing markets as well. So there are a lot of really interesting additional opportunities in terms of what this technology can in fact offer. California. I thought I'd show you this particular picture because CalISO, you don't have any ISOs in your neck of the woods yet. I guess there have been many talks about that over the decades, but CalISO is adopting a regulation market where you have to respond within 4 seconds. In fact, they've changed that to 2 seconds. So you have to have a load that's extremely responsive. That's why PEM electrolyzers or batteries actually offer those opportunities.
Can you explain what ISO is?
So CalISO. ISO stands for, I'm not too sure of the exact acronym breakdown, but it's the system operator. And these folk have a central operating building quite close to Sacramento, and they all sit in front of they sit in front of a big screen, right, that shows their grid and all their producers. And then when they move into the world of unbalance, they turn things on and off. And there are lots of rules and regulations about how that in fact works. So CalISO, ISO New York, New England has an ISO, independent system operator organization that controls the grid stability fundamentally by either providing load or spinning reserve, get on and generate electrons. Okay? We talked about electric vehicles. The market we focus on is pretty much the same as a battery electric vehicle, except that we generate hydrogen that gets stored in a tank and then is put through a fuel cell that generates electricity that drives the wheels. Pretty much the same as a battery electric vehicle, except that you can fill it up in 3 to 4 minutes. Companies that are putting these vehicles on the road, these guys have got cars on the road. The Tucson, they've got about 100 units in California. These guys, the Mirai. Honda has just announced their new Clarity. Audi, Mercedes announced at the beginning of this year. They're all on board. These are the guys that haven't made up their minds yet at the bottom. But those organizations that in fact have fuel cell programs are bringing those cars onto the road. And that's a market again for excess electricity, hydrogen generation that can compete with gasoline or diesel. A few pictures of the cars. The Mirai in the top left, the Tucson, and the new Honda vehicle on the bottom. This is an interesting refueling station. I thought I'd show you a picture of this. This is in Rotherham, quite close to Sheffield. And this particular fueling station actually serves fuel mainly to those cars that ITM in fact own. They own a number of Mirais and they own a number of Tucson, iX35s they call them in the UK. And all of the electricity that is used to generate the hydrogen on site here comes from an on-site wind turbine. It's completely carbon free. There we go. There's a picture of the, oh, you missed it. There's a picture of the turbine in the top right-hand corner. And we also have a number of refueling stations that we're putting in as a company into California. This is at the city of Riverside at their fueling yard. This is at Hyundai's R&D center in Chino. And those two will be coming on stream this year. This is what a typical fueling station looks like in terms of on-site generation. That's the dispenser. That's buffer storage. You have to compress the fuel to get the range. The fuel is compressed, the hydrogen, up to 900 bar, about 12,000 psi. The vehicle's carried around at about 700 bar. Those are the stations we're putting into the UK. We've teamed up with Toyota and with Shell Oil. We've got 3 to 4 gas stations that our systems will be in fact deployed on, just to give you some background information. And we talked about this last night. In the world of energy storage, we no longer have a phone that is a phone. That's no longer a phone. So when you look at it in terms of what the technology offers, our CEO picked this up and he said, this is a really great analogy. If you look at what energy storage is all about, storing energy, frequency control, voltage stabilization when we have a load and we have power conditioning up front, load following, black start, the technology can operate like a battery within seconds, milliseconds. Transmission line investment deferral, again, one of the big challenges we face in terms of the deployment of microgrids or distributed grids. And then chemical feedstock. So when you think of it, it's really interesting in terms of what the opportunities are for the future. Folks, that's it from me. Thank you very much for your attention. Questions?
I guess one of the drawbacks of hydrogen, it isn't readily condensable. In order to make a liquid out of it, you have to go to very low temperatures. So you're talking about 1,000 bars, is that right? Is that, how much can you store in an automobile, for example? How big is a tank and how long will it last?
Okay, we have to switch to metric, unfortunately. The industry actually uses kilograms. So the cars that I showed you in the pictures, they have roughly about 5 to 7 kilograms per vehicle, which gives, well, the Mirai has close to 6 to 7. It has a range of 400 miles. And that's at 700 bar or 10,000 psi in the actual tank. The storage of hydrogen, of course, has been a major challenge, simply because it's such a light gas. And there are newer technologies that are coming out to be able to overcome those problems. Technologies which I talked about with Bob earlier today. There's an interesting chemical process to actually store hydrogen using toluene type chemicals. It's called liquid organic hydrogen carriers, which are extremely dense. It might not be that they'll be on vehicles, but they'll be around to be able to potentially transmit very high density quantities of hydrogen from point A to point B. Are you doing the mic? Okay.
So it looks like you were saying that they could make they could customize it or whatever. So if you do it to power a car, you could do it to have like a generator for your house or whatever. Is that what?
Yeah. So that's exactly what Toyota and Honda are doing. Is they're looking at cars as microgrids for houses, fuel cell vehicles. So that's a 100 kilowatt unit that's got 5 kilograms, 7 kilograms of hydrogen in it. And you can work out how many energy units that is, but they plug that into their house, just like in a plug-in hybrid vehicle, and instead of drawing energy, they can actually provide it back to their house. So Toyota and Honda have selected 2 prefectures, 2 provinces, counties in Japan to do that. Did that sort of answer your question?
Yes.
So another idea to add to the iPhone set of apps. Over there.
Did you say a 90% conversion efficiency from water to hydrogen? From electricity to hydrogen, I mean. through the electrolysis process.
That's correct. So, but I'll just, I'll add to that. The electrolyzer operates, depending upon where you operate the unit, up to about 80% efficiency. But when you look at operating a product like this in a variable type of environment, the averages are around about 75%. Electrical generation to the electrical consumption to the generation of hydrogen and looking at its heat value. The 90% had to do with capturing, because the electrolysis unit has a cooling loop, which is the water, that operates at about 60 Celsius. So you can use that heat energy, and they use that heat energy in that particular case to get the total plant efficiency up to 90.
What's the efficiency of a fuel cell vehicle then?
It's around about 50%. Fuel cell vehicles are about, if you have a look at the Californian Air Resources Board has a number of factors associated to low carbon fuel standards. And what they do is they use a factor of about 2.55 for a fuel cell vehicle versus the efficiency of a gasoline internal combustion engine. So that's roughly the conversion that is used.
Thank you for your presentation. I have just one question, and that is, how is your firm handling the hydrogen embrittlement problems, which have kind of gone along with the storage and use of hydrogen?
Yeah, really good question. So, folks, if you are not aware, pure hydrogen, when it comes into contact with specific, primarily stainless steel type vessels carrying hardware, there is a degradation characteristic called embrittlement, which has to do with the changing of the crystal structure of the steel. So what they've done with that is they have designed specific steel alloys to reduce that drastically where you have pure hydrogen, for example, in fuel cell vehicles or in fuel cells that are stationary. In the case of putting hydrogen into the natural gas grid network, that doesn't work that way. Why? If you go back to a bit of chemistry, methane, CH4, and hydrogen H2, there's a lot of dissociation of the atoms that takes place. So the hydrogen kind of gets stuck to the methane. It doesn't have the same characteristics on the materials that hold it as does pure hydrogen in terms of embrittling the stainless steel, certain stainless steel products that are used. It's still a concern, but I think it's pretty much solved in terms of the technology. Please.
Could you address the possibilities of small-scale applications for off-grid situations? Those of us off-grid often, just like the other Germany, have excess production at some times, and we've always fantasized about hydrogen as a storage for various uses.
So I think the best way to answer that is if you have an interest in ammonia, that is still a very viable proposition. The only challenge is, as opposed to storing this very light gas cost effectively, is you've got a small reactor you've got to make work cost effectively. So when you look at that opportunity, we call those opportunities either remote microgrid systems or remote energy storage systems. And the best example that many demo plants have in fact been tested using the opportunity of gathering excess energy and then converting it into hydrogen with an electrolyzer and then using the hydrogen in a fuel cell to generate electricity. There was one large project in Bella Coola. Didn't work very well because all the products were too immature and there were a lot of failures. Not so much from the electrolyzer and the fuel cell, but all of the power conditioning. Spent a lot of time trying to fix that up. ITM's competitor, our largest competitor in fact, is in Mississauga, Ontario. They have a large project up north, and it pays because up north you have to ship in a lot of diesel. And in many cases, you have to fly the stuff in. So you have power that costs you north of $1 a kilowatt hour. Part of the Glencore group, Raglan mine, which is a rare earth, I think it's a rare earth mine up north in Quebec, is using wind, electrolyzers, low pressure storage, because they've got a lot of real estate, and they've got a 200 kilowatt fuel cell that they're providing heat and electricity back into the system with. Now, I don't think the entire mine is, fitted out with that energy solution, but that's the future in terms of one opportunity that can be used. And particularly, I've got a picture on one of my longer presentation. So batteries do a different thing. A battery converts and stores in the same box. So if you want to convert more, you've got to buy another box. If you want to do whatever, it's a linear relationship, and those batteries cost quite a bit, particularly the newer ones. As you want to actually store more and more and more energy, so the actual cost, capex, gets very, very high. In a concept like this, you have desegregated your generation or your conversion and your storage. You've got two independent aspects. So if you want to put more storage in the form of tanks and cylinders, that's the cheapest solution. So you can keep adding to that, and you can keep your generation, your conversion unit, basically as it is. So when you want to provide energy back in, if it's for grid resiliency or emergency purposes, you have the ability then to cost effectively provide days of energy supply from, for example, a low or high pressure storage in tanks or cylinders of hydrogen, which is what these guys in Raglan are doing. So they've got fuel cells and electrolyzers providing 2 days worth of energy. Batteries gets too expensive. So hopefully that answers your question.
It was more household.
You and me. I don't think there are any companies out there that have household type products available, but I mean, that's the ultimate. I mean, that's what I would. I'd love to have something like that. Photovoltaic, wind.
But your fuel cell car, electric car, would also service that for a household.
Yeah.
System.
Yeah, absolutely. Absolutely. I mean, there have been discussions about home refuelers, right? Small hydrogen generators that you put outside your garage, plug it in, and when you get home at night, fill up your car, and then you make your own fuel. Still, again, very when you miniaturize these things and you generate small quantities, the cost per unit delivered just simply goes up. So we're not there yet, but those are all cool ideas. So those are, I think, the future. Yeah. You're not the only one thinking that way. Yeah.
This all sounds great, and it sounds like it's got huge potential for the future, for growth, for the industry itself. I'm assuming that the water you need for the production of the hydrogen needs to be as pure as possible. I'm assuming that. And I'm wondering if the industry were to grow, what sort of demand that's going to be putting on water supplies and how that affects all the conventional water use.
Yeah, that's a really good question. I normally fire back and I say, do you know how many gallons of water it takes to make a gallon of gasoline? Google it. It'll surprise you. We use far less water in electrolysis, for example, for fuel cell vehicles, by providing the hydrogen than we currently need to produce a gallon of gasoline. That's California, of course, right? Drought years. They always talked about it. Purity of water, drinking water. What we do is we have filters on board, the actual electrolysis units that take out the unwanted ions or chemical species we don't want. But Google that. How many gallons of water do you require to make a gallon of gasoline? It's quite surprising. It's a whole lot more than people think. Yeah.
A supplemental question, a follow-up to the last question. When you burn gasoline in a car, the car has a tailpipe. A certain amount of water is returned to the atmosphere in the form of vapor.
Yep.
A hydrogen car doesn't have a tailpipe. Is that water lost forever once it's electrolyzed?
It does have a tailpipe. It has a tailpipe.
Explain, please.
Pardon me?
Explain, please.
So the tailpipe out of a fuel cell vehicle. So what happens is that in the actual fuel cell unit, inside the vehicle, and I took the picture of, I'm sorry, that was part of my long presentation. There is a fuel cell unit that gets supplied with air and hydrogen, and it generates heat, electricity, and water. And the water comes out of one of the sides of the fuel cell, and it simply gets fed into, because it's under pressure, gets fed into a tailpipe and comes out the back of a vehicle, or comes out the top. There were 20 fuel cell buses in Whistler, and if you, the actual tailpipe, as in a usual diesel-powered bus, comes out the top and goes straight up, and that's just water and vapor, or water, condensed water and vapor that comes out. So there is a they do have tailpipes. Yeah. What happens to it goes back into the atmosphere, so it's recycled. Thank you. Okay, you're welcome.
Hi, I have a question about the grid. You said that with natural gas that the hydrogen could be added to it. It's still natural gas,
Yes.
but it's less gas and more, and sort of like
Yes.
diluting gasoline
Yes.
with biofuels, that kind of concept?
Absolutely.
Okay.
So diluting the natural gas components, or methane being the primary one, with a bit of hydrogen, which carries that green badge around with it. That's really the concept,
Okay.
right? Yeah.
And then I had an idea. I used to be an airline stewardess, and I was wondering if we couldn't be using all the wind that's going over the wings as some kind of a fuel source.
I've got some guys at Airbus. I'll introduce you to them. Yeah, absolutely. I don't know the answer to that question. I really don't. But if you like that kind of stuff, go onto the Airbus website and then type in hydrogen, and you'll see what they're doing with fuel cells. It's really cool. They've got movies. So the water they generate on the plane, they use for drinking water, or they use for toilets. That's the plan, as an idea. That's in the movie.
Questions?
So kind of going back to the question about the household, excuse me, the household side.
Yep.
Size. A little bit larger, in your presentation you showed a fueling station that was solely powered by wind.
Yep.
And I know one of the challenges with any of these new technologies is getting the infrastructure in place. We've got a group here in town working on getting electric charging stations.
Right.
So what is the requirement for a standalone station like the one you showed? What does it take to actually generate enough hydrogen to make it like a standalone station?
Lots of fuel cell cars.
Right,
Utilization
but,
is the key.
How much solar, how much wind, what kind of
okay.
power input does it take?
So we require roughly 60 kilowatt hours to produce a kilogram of hydrogen. Does that help you? So a kilogram is the equivalent of a gallon of gasoline, ballpark. So if you go back to those equivalency factors between fuel cell vehicles and gasoline-powered vehicles, so roughly about 60 kilowatt hours out of an electrolyzer, which with its parasitic load and all the stuff around it, is required to generate a kilogram of hydrogen. Okay?
So can we go back to the water for a minute?
Yep.
I didn't quite hear how pure the water had to be, but in my imagination, the issue that has been rumbling for at least 50 years, in my recall, has been all around sewage treatment plants.
Yep.
And it seems to me that your concepts and sewage treatment plants could have a great marriage.
Absolutely. That's exactly what that company, Fissmann in Germany, is doing. If you go and speak with them, they've got a map on their wall, the guy that heads the company up, and he's got every single wastewater treatment plant in Germany on a map, and those are all of his target customers.
For methane and for water?
So when you go to a wastewater treatment plant, you've got two parts of it. You've got the aerobic side, the big ponds, right? Then you've got the anaerobic digesters. You either burn the material or you put it through anaerobic digestion. Anaerobic digestion generates two major gases, primarily methane and a fair amount of CO2. So what they're doing is they're targeting with their special bugs and systems to actually add hydrogen and combine it with the CO2 using bugs, using microbes.
and generating more hydrogen.
Yeah, about 97 to 98%. Yeah.
I'm sorry if I missed
No, generating 97 to 98% renewable methane, not hydrogen. They use the hydrogen together with the CO2.
My point was the original generation of the hydrogen that
Yep.
you're using in all of this.
Yep.
There's the water, we're often told it's still drinkable, and there's all of the bio.
Oh, you mean the byproduct water that comes out of our system? Did I get it? Yes. Yeah, you can drink it.
Well,
Not a
and then
byproduct
can you
water
make
from
the
the sewage
hydrogen?
treatment.
Sorry, I'm getting a bit confused. Let's go through.
And can you make the hydrogen with it?
Yes, you can. Yep.
Questions?
Could you put 1 kilogram of hydrogen in perspective, like equate it to gallons of gasoline or, something
Yeah.
like that?
In terms of how much it cost?
No, in terms of what it'll do.
Oh, okay. So the comparisons that are used in the automotive industry are very simple. What they've done is they've said 1 gallon of gasoline in a gasoline-powered vehicle is equivalent to a kilogram of hydrogen in a fuel cell vehicle. So the fuel cell vehicle has roughly 2.5 times the efficiency. And when you asked me the question, I thought you had also talked about, or I was thinking that you were thinking about price. So the price of 1 kilogram of hydrogen needs to be roughly the same price as a gallon of gasoline to make it equivalent. Ballpark, sort of the ballpark figure. But that's the relationship is it's got to do with the efficiencies of fuel cells versus internal combustion engines. It's roughly 2.55 times more efficient. They call it the equivalency energy factor, the EEF, that the government folk use to do their calcs.
Questions?
Thanks a lot for coming and speaking here. It's very nice of you to do that. Are there any health and safety issues with this? And also, are there any issues with regard to waste?
Health, I guess if it has to do with safety, yes. Like any gas or any liquid fuel or anything that has a hazardous characteristic, without a doubt. Hydrogen needs to be handled correctly in terms of the codes and standards that have been set. We have to remember that hydrogen has been around for a hell of a long time. It's been used in the chemical industry for decades. So it's not new. What is new is putting that as a fuel source on board or putting it in places that we haven't put it in the past. So there are rules and regulations that are associated to things like if you've got in that picture of the fueling station, what the distance is between the sparks and the gas side, what you have to have between certain things. So there are rules and regs that are set up. The Department of Energy has a really cool and informative website that provides you with all the details associated to that for a fueling station or any type of on-site generation or handling system. The last question was...
waste.
No.
See that you were mentioning methanation and ammonia. Typically, I think of these processes involve a certain amount of waste that could be hazardous.
No. I mean, the waste from hydrogen in a fuel cell application, or even when you burn hydrogen, in the atmosphere is water.
It goes back.
Yeah, it goes back into water. So there's no waste from that pathway. Generating ammonia, there's no waste. There's no waste product other than, ammonia that escapes that shouldn't escape, that you need to use. Yeah.
And the same with methanation.
Yeah, so methanation is a bit of a... there are billions of dollars, euros invested in natural gas grid networks. So those folk that have invested want to use it. But what they put back in there is, of course, methane. Methane is a greenhouse gas. Right, so that's one of the concerns. That's one of the sort of the balancing acts that, when you think about SoCal gas, did any of you folks see that leak that took place? Yeah? So that's the concern when it comes to using those infrastructures to deliver energy to us. Even if it's in a clean form and it escapes, it's still a very potent greenhouse gas as such. Okay, then one last comment from my side. Thank you very much for the opportunity. My home's not too far away from you folks. I'm sort of a little bit north of Victoria on the island, so on the east coast. So my first visit to Port Townsend. So thank you very much for the opportunity to speak to you today, speak with you. And thanks for the questions.
Welcome to Port Townsend, and thank you for coming.
Thank you. You're most welcome. Thank you.